Yeah, so far we've had only academic presentations, right? People from universities, professors, so this will be the first time we have industry person presenting. So Nabeel Mehdi from Support Logic, a California company. Although he lives not very far from here in the Detroit area, he works remotely, but he's going to talk about cyber-physical security. And it's my pleasure.
So let me begin by thanking Dr. Daniel and Dr. Javed for inviting me to participate in this seminar. My name is Nabeel Mehdi, and I am a senior software engineer and a data scientist for a startup based in California called Support Logic. The presentation will be on the topic of cyber physical security threat models in industrial systems, and I'll be sharing some experience and some projects about that I've worked on and are currently in production. So these are some of the my professional associations. I have worked with these small companies, small startups in India, in Middle East, and India, and also I did my master's from NC State University. So you'll see that logo over there. Presently, I live in Michigan with my wife and two babies, as you can see in the picture. One of them is 6-month-old, and another one is 1.5 years old. So there's something special about babies, right? Babies are delicate creatures. They don't eat pizza, drink coffee, or donuts like we do. They have a special requirements, right? They just have milk. They have infant formula, right? So over the last 6-7 months, in fact, over 1 year or so, there has been an extreme shortage of baby food. I don't know if you're aware of that, across whole of North America. And it's been said that there are supply chain, it's because of the COVID global supply chain crisis, and also a manufacturing plant of the infant formula in Michigan called Abbott was temporarily shut down. So because of the ripple effects of that, till now, it's very difficult to find baby formula. In fact, at one point of time, we had to drive to Canada and try to get that, and we are not alone. There's so many others who are facing the same issue. So I use this example especially to specify how much fragile, limited, and vulnerable our manufacturing and supply chain is. I know if I were here from, let's say, representing Google, Facebook, or maybe talking about ChatGPT, that would have been much cooler presentation, right? But then this is actually, if you look around us, the chair you're sitting on, this laptop, the car that we used to drive in, everything has been built in a manufacturing plant. Ultimately, even the foods that we eat have been processed through a factory and reached us through the supply chain. So that's the reason of, that's the theme of this presentation. And also you can imagine the implication that just like this baby formula factory, in the future, if there is a similar scenario with other pharmaceutical companies, let's say, if there's a shutdown, then it will have the power to bring the world to its knees. So the agenda of this presentation, I'll try to start with talking a little bit about CPS, manufacturing industrial systems, and then some vulnerabilities and security challenges based on my experience and my learnings in the sector. And then I will be sharing 2 real-world examples about the projects that I've worked on in the past related to this theme. And finally, we'll have a question-answer session in which I'll try to answer most questions unless it's something that violates the NDA and confidentiality agreements that I have. So let's begin with the first slide, which is what is CPS, or Cyber Physical System. So National Science Foundation defines cyber physical systems as those systems that integrate sensing, computation, control, and networking into physical objects and infrastructure, connecting to them to the internet and to each other. So that's the theoretical level definition. Another way to present it or to describe it would be what I think is CPS is the fusion of information technology plus the operation technology plus the engineering technology. So as computer science students, I think you must be more familiar with the IT side of things. And if you talk about the OT, which is the operational technology, you can see there are 2 diagrams or 2 images. One is SCADA system, which stands for Supervisory Control and Data Acquisition System. So which is nothing, basically, that's a software application that the operators use in the plant or in any manufacturing facility to control, to monitor the plant equipment and the plant processes. That's the screenshot of that. And below that is an example of this control panel, basically, that can be used to start, stop, or any basic operation. On the right side is the engineering technology. Under that section, you can see the image of PLC. So PLC is basically the heart of any facility, whether it is a manufacturing plant or if it's a processing unit. So PLC stands for Programmable Logical Controller. So if you are familiar with Arduino and Raspberry Pi, so this is like the big daddy of that, which is used in industrial settings, where the designer implements the logic, inputs, connects the inputs and outputs at the factory. So the difference between that, one question that I used to have when I was a student is why not use Raspberry Pi or an Arduino instead of the PLC, is that PLC is made to be resilient and robust to extreme conditions, to extreme weather temperatures, and it's highly reliable. So it's the industry standard, what I'm trying to say. In any facility, you will always see these 4 or 5 elements. And below that, another key component of any industrial system is the actuators and sensors. Here you can see just an example of a few sensors and a pump. So whichever facility that you visit, you will always find the sensors and actuators. So overall, the cyber physical systems are challenging due to the intricate interplay between these physical and digital components. And that's what makes them difficult to design, deploy, and also secure from the security point of view. The good news is there's already a standard, global standard, or which is there, that can be used to categorize or group these different components in any plant, in any manufacturing plant or industrial unit, where you can segregate the different components in these 5 levels. This is a very famous architecture. It's called ISA 95, also known as the Purdue Enterprise Reference Architecture. And what it shows is that you can see at level 0. So level 0 is contains all the factory equipments and the actual process that is happening. And the operations here, or the events or the decisions here, happen within a fraction of seconds, like milliseconds. For example, if there's a valve shutdown or valve opening, that's what level 0 denotes. At level 1, there are sensing and manipulating capabilities, all the components that guide that. And there you can see the PLC that we just discussed in the previous slide. And on level 2, there are the monitoring and supervising components, it's like SCADA. And then above that, there is the level 3, which is any other tools that the factory may be using, for example, for maintenance, scheduling, and all that. And finally, at the top are the ERP systems, where the key stakeholders decide or make decisions looking into the horizons, like what's the demand going to be in the next 2 months. And then they make up the plans, and basically that trickles down to the level 0. So all these are interconnected, but however, it's a complete segregation of these different components. The reason for showing this is, if let's say you are a malicious actor, then there are different avenues where you can attack them. Or if let's say if you are trying to secure the system, you need to be aware of these different components and these different levels. For example, if at level 0, let's say the sensor calibration gets off, then it may end up, the plant may end up, or the machine may end up dosing more chemicals than it would have, taking that a different step as it would have if the calibration were correct. Similarly, if the maintenance protocols at level 3, let's say someone tweaks that, instead of this machine doesn't need to be maintained every week, it needs to be maintained once in 6 months. Someone tweaks that information, and let's say, so what that can impact is the machine life, equipment life will be reduced, and it will ultimately be a loss of resources and money for the company. So the reason for sharing this is, I know this is boring. I can see a couple of faces yawning at this. I know, I can understand that. So let's imagine a scenario, right? You are hypothetically outside the sun, and you're sitting in the park with your family, and having a good time, playing around with the kids and eating pizza, and suddenly, let's say the entire park gets flooded with sewage, bad smell, and all millions of gallons of sewage from the houses, and it's floating around. How will you feel about that? So what if I tell you that this actually happened 22 years ago in Australia, where a hacker, he did was he hacked into the sewage management system of the park of that area, and then he broke into that system, and he tweaked the pump activity to cause this massive spillage that resulted in the loss of marine life and groundwater pollution. And also there was an unbearable stench in that area for several days in the future. One thing worth mentioning here is that the hacker who was able to get into the system, he already had that knowledge. He himself was a wastewater operator, so he knew where to attack. He knew what should I need to do to get into this and to trigger this. If it were a general, someone not from that background, it would have taken them much more, it would have been much more harder for them. So this is like 22 years ago, and let me give another example. This is 2 years ago. This is in Florida. Someone remotely accessed the water network and tried to increase the chemical dosage of the water pipeline, which 15,000 people were receiving in their homes. So thankfully, it was caught by the operator, plant operator, that this is some anomaly going on, and that operator was able to stop that and identify the hacker. Identify that attack. If that attack was successful, so theoretically, about 15,000 people would have been poisoned by this. So the reason this keeps on happening is because in this 20 years time frame, although we have moved from Windows 95 or Windows XP to whatever Windows or 12 or whatever the current version is, but in the plant itself, they may still be using Windows 95 or Windows 98 systems to control their equipment, because it costs a lot of resources, it costs a lot of money to make those upgrades. If I want to buy a new laptop, I can simply go and throw my old one. But if the laptop or if the system is connected, if the application, the SCADA system is only compatible with Windows 95, then I also need to upgrade those softwares and everything to support that. So that's the reason why this keeps on happening. And as more control systems become computerized and internet connected with the so-called Industry 4.0 benefits, the dangers from hackers and even terrorist attacks are increasing day by day. Especially critical infrastructure like water and wastewater management systems are vulnerable because they continue to use outdated technologies that directly touch the lives of large populations. So let me just summarize a few challenges and vulnerabilities in these. The first one is, as I already talked about, they could be using these plants and these facilities could be using legacy systems, which are very expensive to replace. And in some cases, it's not even possible because the company who built the other software, the operation technology application or MES, that doesn't exist anymore. So who is going to upgrade that? So what ends up happening is they still continue to use Windows 98 or 95 to support those plants. Second point is rotating workforce. So usually at these manufacturing facilities, as well as these plants, the workforce, there are a lot of contract workers and temporary workers who may be joining them and then leaving them. And that makes the line or the system vulnerable. Thirdly, there are complex custom integrations. So if you recall the first or second slide, there is ET, there is OT, and there is IT systems. All of them may have a different OS, all of them may have a different different kind of programming. For example, PLC uses ladder logic programming. SCADA could be built on, let's say, C++, and the operating system is using some other OS. So that's why it's very expensive to make these integrations or to change them. I worked with a company that wrote the code comments in Swedish. So I wanted to, this is like 5 years ago. There was a company I worked for, they have this Bueller, basically the name is Bueller. And the equipment, they had the code running, I wanted to look at it. Even the variable names, they were using on their own language instead of using something like English. And it makes sense, because if something breaks down, instead of we solving the problem ourselves, we have to pay them and get them solved. So that's why these companies who make these hardware and software, they make the code deliberately cryptic, and they can make it very complex. So if something breaks down, you can't fix it. And also, there haven't been much investment. It's kind of a new field because of the integration. I wouldn't say new, but the challenges and the explorations in this is fairly new topic, and it's gaining importance now. And again, there are a facility is susceptible to both front door, back door attacks from external and internal threats both. Also, there are less tools for monitoring, very less research and generic tools to be able to identify these threats and issues on different hardware and software both. So, and then the cryptocurrency has basically insensitized or encouraged these malicious actors, because now they can anonymously inject some ransomware or hijack a plant or a critical infrastructure, and very easily they can get the return out of it. So that's why these threats seem to increase as well. And finally, Industry 4.0 use cases. So earlier what happened is these equipment and these internal networks used to be completely blocked from the outside internet. But now, since there are a lot of data science activities, AI stuff going on, so people are connecting their plants to extract that data from equipment in real time to improve their productivity and optimize their operations. So this opens up different avenues and areas where the threats can arise from. So I'll quickly try to talk about the water cycle and why this is important and how that works. So while we are sitting here, we don't comprehend that underneath us there's a whole network of pipelines and pumps, which easily brings us water to the taps and also takes the outgoing sewage or waste from the washrooms to the facility. So how that works is, if you can see at one, the water is first taken out from the freshwater sources of any water bodies. It is purified in a plant. So it's a high-level view. I'm not going to deep dive into it and try to boil the ocean. But in the purification, there are so many chemical, physical, and biological treatments that the water has to go through before it reaches us. And again, those treatments and those operations, coming back to slide 2, they are controlled using PLC, sensors, SCADA systems. There must be some operator and actuators, right? So those kind of things are still apply on this. Once the water is cleaned, once the water is being purified, it reaches us through pumps and underground pipelines, and we are able to use it. Similarly, the waste that we release from the washrooms, it has to travel through a collection system network. So again, that collection system has underground flow meters. There must be flow meters here, right? We don't even see. There must be a pump station somewhere that's pulling that water, wastewater. And it's taking it to the wastewater treatment plant. And that plant also has like a lot of operations, which I'm not going to talk about now. After treating that wastewater from that we release, it's separated out into solid components and the water component, called as the effluent. So that effluent, which is the water component out of the retrieved water out of that sewage, that needs to be released into the water bodies. The tricky thing about that is it needs to be treated, so all the bacteria that we have released, it needs to be killed before it goes into the marine body and pollute the marine life. To do that, just for an example, there's a process called chlorination. So what happens is there's a chlorine treatment that goes on into it, And the tricky thing is, if you add more chlorine to it to kill the bacteria, that chlorine becomes harmful for the marine life. If you don't add enough chlorine, on the other hand, then it doesn't kill the bacteria or the E. coli, and it ends up polluting the, or maybe killing the marine life. So it's a very critical step in that. And again, that is controlled through this automated system. It's not something that someone is dosing it manually, right? There is a code that runs behind the scenes, and that code opens up the valve. That code senses the takes the reading from the flow meter, and does all that kind of computation, and basically decides based on the flow, incoming flow, based on how much dirty the water is, that how much chlorine I need to inject. So that's just one example of, I wanted to explain how this water cycle works. And I worked with utilities, water and wastewater utilities in Michigan, in New York and Indiana in the past. And what we did is we deployed different machine learning models based on historical data from these utilities. And those models basically look at different real-time parameters like the flow rate from the flow meter sensor, the weather from the weather API, so how's the weather today. We also look at factors like what's the date today. If it's Christmas, then you expect that if it's Christmas and it's a college college campus region, then the students would be gone, right? The flow would be different, and the wastewater component would be different than let's say any other residential place where more people would be there during the Christmas time. So we have to look at those factors as well. And then things like sludge density, what is the temperature like, how much is the TSS, and many others. So I cannot talk more details about it, but I can describe you an overview that looking at these real-time sensors, I've built models that are able to detect any anomalous behavior. So let's say in the previous example of Florida, the operator caught it manually, right? What if the operator was not there? So what this model does is it looks at it looks at these parameters, and it decides a range that if the chlorination, for example, is within this range, then it's fine. If it is going beyond it, then it triggers an alarm. So that is one thing. Second is recommending the chemical dosage quantities. So as I mentioned earlier, if the chemicals are a tricky thing, if you add more, you're wasting money, you're wasting chemicals, and it can also lead to damages. If you're dosing it less, then it's not serving the purpose. So we built a model to do that. And then predicting the real-time sewage quality, forecasting flows. How is the flow going to look like tomorrow, right? So let's say tomorrow is Christmas, and last year and during the Christmas time, this was the flow pattern. How is it going to be today? So the model basically predicts based on that. Similarly, identifying the underground pipe breakage. So as I mentioned earlier, there's a whole network of underground pipes that brings us water and takes the sewage away. So there's something called I&I, infiltration and inflow. When the pipe breaks, that condition happens. So we build models to be able to predict it without a sensor, just looking at the flow, what's the flow rate and how it's coming. And then finally, equipment health monitoring. So that's an easy use case. That's a very standard use case. So these are 6 different model types that we built, and they are currently running in production and helping the plant operators to optimize their operations. So that was the first example, if you remember the agenda. The second example is, let me switch the gears and talk a little bit about manufacturing. I think we still have time, and I'm speaking quite fast, so we should be able to wrap this up. So manufacturing sector, right? So we understand everything around us is coming from a manufacturing unit, right? No matter how many hours we spend on Instagram, on Facebook, ultimately we have to eat something, or we have to sit on a chair, we have to drive our car, and everything is related to that field. So what makes the sector vulnerable? So if I ask you, who built this car? You're going to say, this car was built by Ford, right? That's the obvious answer. This is a Ford Fiesta. But then if you look closely, these are the different companies that built each part of that car. So these are the subcontractors and contracting companies that provided the parts that when they came together, it's called as Ford, Ford Fiesta. So what that means is there must be so many different manufacturing facilities that are building that part, coordinating with each other, and ultimately providing Ford that parts. So that's how it works basically in every industry. Even if you're eating a food item, for processed chips, let's say, so some of the raw material, a few of the raw materials could be coming from Ukraine, other one would be from, let's say, India, some other from Turkey, for instance. So what that means is if any failure points, so these contractors are introducing failure points. If any one of them fails to deliver on time, or there's a quality issue, it ultimately reflects on the bigger part. So although in Industry 4.0, these contractors and their facilities are being can be remotely monitored. Their equipment can be remotely monitored by Ford Motors, right? Sitting here, they can look at the other plants, how is it working? But that is not enough to for some threats that I'm going to quickly talk about. Before listing them, let's quickly review how the manufacturing works, right? So everything between supply and demand is here. So if you look at this, it begins from the top. There's a demand. So let me continue with the Ford example, right? So let's say Ford orders, a certain part, right, with a supplier located in, let's say, in another country, in China, for instance. So the first step would be designing that part, the product design, right? So that design could be either Ford could provide that design, or the supplier themselves could be, designing that and proposing it to Ford. So the first step is product design. The second step is to procure the raw material. Then the supplier will decide, or there will be a team that will decide, okay, we have to build 50,000 parts. How much raw material will that entail? How much raw materials do I need? And after that, once the raw material is there, you have to inject or set up that design into the machine, decide which machine will that design go into, and write the code. So if you can see, this is a program that goes into this machine, and it's different than what we have in the other programming languages. So once that has been decided, the supplier sets up these different equipments, and on a scale, and basically all the protocols, safety protocols, quality protocols, and then the actual production happens. Once the 50,000 parts are built, then statistically, a few of the parts are taken out of that, that whole output, and they are tested. Some stress testing is done, or any type of testing is done, and basically to get confidence that the parts follow the quality or not. And then once the parts are ready, they are generally stored in a warehouse, packed and stored in a warehouse under the inventory management section, 6 number. So it has its own, it has its own basically nuances. I'm not going to get into that. And when the part is in the warehouse, it finally, after some time, it goes into the truck, and it reaches the destination. So let's say it reaches the Ford assembly factory, right? So that's where the supply begins. So any product that you can think of, whether it's be a car part or it's a food processing unit, all of them will be following these, more or less, these steps that are over here. So now, having said that, let me talk about the special case or the threat, one of the threats in this scenario. So I mentioned earlier that Ford could be remotely monitoring those factory supplier equipment for the health and all those operational data. It could also be looking at the report. The supplier would say that this is the report that this batch was produced on 2 months ago, and this is the new batch, and so on and so on. So what if the supplier decides to cheat on Ford, right? What if they decide to, because they're getting paid for it, right? And so you can see an example here. There are two similar parts, two identical parts. One has been printed, one has been made on a $150 equipment. Another one has been built on a $5,000 equipment. So the price of these would be substantially, very different because they have different costs. So let's say Ford wants the supplier to build this part on the $5,000 equipment, right? It has a higher finish, higher tolerance, and better quality. So Ford and the supplier agrees. They say that, yes, okay, I'll make the 50,000 parts on the 1,000 machines that I have, and it will be of a high quality, right? Now it's humanly not possible to inspect each and every part, right? 50,000 parts are there, you cannot check each part. So they have to rely on what the, what the supplier is saying. What if the supplier decides to, or what are the ways in which the supplier can cheat with the Ford, right? So these are a few threat models that I have mentioned here. Beginning with the top one, so just like you have those phishing attacks and those kind of attacks in the pure, cyber security domain. Similarly, these are the threat models in the digital manufacturing. In this particular case, the first one is the ghost machine. So let's say I'm a Ford manager, right? And I call the supplier. I say, hey, how's the production going? Are you on track? And the supplier says, yes, you can check the dashboard that we have shared with you. You can see the status of the machine is on, right? So I look at it, I say, yeah, I'm confident that the machine is running right now and the production is happening. But what happened on the other hand, the supplier removed the machine and somehow replaced it with a simulator, right? So instead of the actual data, I'm seeing a simulated data, but I don't know that, right? So that's the first, which is the ghost machine. The second one, the second threat is the substitute. In this case, in this scenario, so the contractor has agreed that I will make the part on a $5,000 machine. But when the actual production happens, they replace it with a substandard machine, poor quality machine, right? And they don't inform me that they have done that. And again, so since the digital fingerprints and the digital signature can be forged, they do that, and I don't learn that. Third one is the Walking Dead scenario. In this, the machine has been, it's in a very wear and tear, bad condition, right? It has not been properly taken care of, but the supplier continues to make parts on that without following the protocol. And finally, the fourth one is cook the book. In this case, the supplier tells me that, oh, we are very busy. We have 1,000 machines, but 950 of them are currently busy. We just have 50 of them, and we won't be able to meet your order. And we want to raise the price because it's, we don't have that many machine. If you want, that you have to send, give us more money for that. In that case, the supplier will, falsify the metadata, all the, outputs, and again show us the dashboard maybe that see all of them are busy. So these are the four threats, and it's very difficult to be able to identify them from the customers or the Ford's point of view. So one solution for that is, I should say, this was part of my research, not a solution, but something that we proposed is what we called a witness box protocol. And in this, we propose to create a digital fingerprint from the physical parameters of the machine. So whenever an equipment runs, it emits certain sounds, certain frequencies. It has certain vibrations. Just like we humans, we have a heartbeat, right? Heart rate, we have a body temperature. We have certain parameters that are inherent to us. So using that signature, Ford can validate that this was the actual machine signature and not the other machine. So if that signature is, if the Ford manager is able to see that signature online, or if there's a device that senses it and is able to validate or authenticate that device based on that signature, then that should solve the purpose. So we used something called locality sensitive hashing. Most of you must have heard of it. So unlike the typical hashing, which tries to minimize collision, locality sensitive hashing tries to maximize that collision. So I'll tell you the reason for that is when we run, our heartbeat increases, right? Or if we age, grow up, then there's a difference in the pattern, heartbeat pattern that we have slowly changes over time. Similarly, when the equipment is running, due to wear and tear, the magnetic energy it radiates, the sound it makes, and those kind of physical parameters, they change slowly over time due to that wear and tear. So the hash that will generate, the fingerprint that will generate from those parameters would slightly keep changing. And using Jacquard similarity index, we were able to match those. We were able to match those signatures, that this signature belongs to this machine and not to the other machine. And using that, we demonstrated the identification and authentication of that equipment on the network. And it was purely based on the hardware signature and the performance of the machine. So on the right side, you can see these clusters, and each cluster represents one equipment that we tested. And within that, there are different signature points. It's basically, I have projected it on a 2-dimension just to be able to visually see it better. So as you can see, there are 6 different equipments here, and we were successfully able to show their signature. So with this, let me leave some time for questions. We just covered a little segment of the threats that are relevant to CPS. There is a whole lot of different scenarios and various areas where we can talk about more about it. So, but hopefully, you got the idea and enough understanding now about this field, about the challenges, to delve more on this theme. With this, let me wrap the presentation and open the floor for questions. So thank you.
Okay, thank you. Questions from students?
I apologize, I had to run fast because of the time. I tried to be fast.
Yeah. Again, like a 12 hours.
So, do you think making the control system artificially intelligent, using machine learning to handle the control systems and keep making it isolated from the outside world as much as possible, will keep it secure from cyber-physical threats?
Right, so that's a good question. We have tried to do that. That's a real world problem. The thing is, there are two things basically. The first thing is, what type of AI we are talking about? Is it a black box kind of model, or is it something which is predictable, or you understand how and why it's predicting something? There is a danger with using a black box kind of control system based AI. So that's one thing that needs to be considered in that. And secondly, it is best to use AI right now in these safety and safety processes and quality processes as an auxiliary and not primary driver of the system. So it's good. So all the models that I talked about, none of them are leading the process, or the dosing is not completely following that model's prediction. There's not enough confidence yet. But what it does is it informs the actual supervisor, actual human being, that this is the dosage. Do you want? I recommend. That's what the model is telling the operator, and then it's the operator who has to decide, whether I want to follow that advice or I want to follow my instincts. And ultimately, I believe they will reach a point when the operator gains enough confidence that this model is right. Then they may let it drive the system. Who knows in the future? But for now, yeah, that's answer to your question. Yes, that will be in an ideal world, that will be an excellent idea.
So my question is, you have talked about 2 different scenarios. One was the wastewater management, right? First one. So where you are trying to control several outputs, like trying to flow, malicious flow in the marine life, or trying to predict the amount of chlorine in the wastewater things, and there were other parameters as well.
Right.
So my question is, the model when you try to take, so you, to me, as I understood, you have like a different logic to deal with all these 4 or 5 parameters which you are trying to say. Like if this is chlorine is this, then this, or if the flow is this. So is that correct? So you have separate kind of a control logic, I would say. So machine has some kind of thing for 4 different parameters.
Right.
Not taking all these 4 simultaneously and doing anything. No, they are all independent. So that means you have a different logic to control the chlorine flow. You have a different logic to predict the sewage flow. You have a different logic to predict that. So you treat all these input parameters which you create, and you have separate control logic for each one.
Yeah, the models were different, but then they had certain common inputs to them. For example, the flow, and there were also some interdependencies. Like one, if the flow, let's say the chlorination is this much. Or basically before the chlorination there is other steps like sludge retrieval and all that. So one model is predicting how much how much is the sludge content, right, sludge density. So that's sludge density before the model. Before we had the model, it has to be physically tested by the how it worked is someone will take the sample, send it to the lab, and the lab will give a result that this is the density. So we took the data for the last 2-3 years, right, and trained a model to be able to predict the density without going to the lab, right? So if looking at the historical inputs, so we were able to eliminate, or I would say eliminate the need to immediately test the sample to predict the density. We were able to, the model was telling that this is the density. And then based on the density, the next step is to predict the chlorination, how much chlorine you need to add. So that's the second model. I don't know if that answers your question. So there is, it's not completely independent. There are interdependencies, and there are several common inputs in these.
Okay, so another question was like this production system, you are trying to see whether the machine is fake, or you are trying to test it whether there is noise and other scenario. But isn't that true? Like, if everything is what they claim is running, then you should get the product on time. If the product is not on time, then we will know that their machine is actually not running or something.
Right.
So,
yeah,
the question is like, if all those things they are doing, but your production is not coming on, reaching you on time, then you can say that this particular model is fake.
Right.
So I think I forgot to mention that point. The actual reason for that scenario was the contractor 1, we have given the order to contractor 1 that you have this equipment and we need 5,000 parts. What they do is they subcontract that part to another contractor, right? Let's say they act as a middleman. So we are looking at the data, we are saying, okay, the machine is running and we even get it on time, right? But that part, they actually did not make it. They subcontracted it to a third party and they didn't inform us. So I think that is the more appropriate reason for that scenario, why they will do that.
But then the product will have different tolerances. It should not be acceptable if they subcontract it to somebody on a kind of.
So as I showed that diagram, it's very, it can be difficult sometimes to distinguish, and maybe they just, subcontracted a little part of it, not all the 50,000 parts, but maybe 2,000 parts they did. And if you look at it in a high level, it doesn't look that much difference. It's at it's at the micro level kind of tolerance levels that we're talking about. And the product may be at par with the quality, but actually you charged for something else, right? It may be that the qualities are almost same, but still the contractor is charging them for this $5,000 equipment and not the actual one. So I hope that answers, yes.
So I'm not sure whether you can answer this question, but you talked at the beginning about how critical infrastructure still uses obsolete operating systems or software like that. So that seems like a very big problem. I'm hearing left and right that it's not only water plants, but any critical infrastructure, right?
Right.
Even energy companies, even DT, all these using older. So then doesn't it make to have legislature laws that basically require the software companies, Microsoft, to maintain their older systems for a longer time? I mean, Windows 10 is going to be supported for another couple of years, and then they're switching to the next one.
Right.
I mean, I think that's a big problem.
Yeah, that's a
So
big point.
Microsoft should be required to maintain it longer, at least for maybe create a small group that maintains this for industrial systems, for critical infrastructure, things like that.
Yeah.
So have you heard anything about that?
I haven't heard about that, but on the other side, I mean, which still is relevant for your point is, government does provide annual, capital to these critical infrastructure, these units to upgrade their systems, to upgrade their whatever. So that's dedicated. That amount is dedicated for the upgradation of these software applications.
But sometimes that's not enough.
That's not
because
enough,
You have
yeah.
to basically upgrade also the hardware, and that
Exactly.
becomes much more expensive. Probably the government doesn't provide that money.
Yeah.
So,
Yeah, that's a good point.
and obviously the software company has the interest to keep changing that and making these periods shorter and shorter,
Right.
coming with new products that they don't, and the old one they don't maintain. So I think that's becoming
Yeah.
a significant problem. I mean, you're more on their side, I guess, but not quite, right?
Right.
Yeah, another thing on that is government does have, there have been there have been some legislatures on open sourcing or using open source, models or data acquisition, languages, for example, MT Connect and OPC UA, instead of writing something so cryptic, something which the company has the IP, so other companies not able to, troubleshoot that or maintain that. So I think once that happens, that transition is happening, by the way, slowly. I see new, I would say, robots or the CNCs using those open source protocols like MT Connect, which are, by the way, there on the NIST websites in the recommendations, and they have a test bed for it.
But then the open software, isn't that more vulnerable to cyber attacks being open?
Yeah, that's. I think that's a question. Again, the same question about Linux versus Mac or that kind of thing. That's a whole different debate.
Yes. Okay. Any other questions?
So you got some questions, yeah?
Yeah. So it's just a basic question about controls. What control strategies did you use? Are all those were all those open loop or closed loop? And if open loop, then the operator has to be there to make some changes. And what are the control strategies?
Right. So I guess you are referring to this. So in this case, as I said, we did not directly tweak the utilities, and any facility still doesn't have any confidence. I think that boils to her question as well, that we don't directly connect the models to the control system yet. So we have a separate isolated cloud-based platform that was able to read the inputs using the their database, and then database goes through SCADA. SCADA connects to PLC. So using those inputs, and we were giving an output or these results on the platform itself, that can ultimately go into the control system, and however it is designed, it has to go into that. So I don't have a clear answer to that. But on the industrial, if you ask on a general level, what are the control systems used? There is something called PID, that is the proportional integrate. Electrical engineers are, I think, very familiar with that. PID controls, which is very common across all the plants.
We had a famous, I can say, stuck snake attack back in 2010 for the PLC. I think it was in the Iran or somewhere in the nuclear power plant. And after that incident, what are the major things that is done in the field of, particularly in the field of SCADA and PLC system, to eliminate those type of cyber threat?
I think I don't think so. Anything major had been. I'm not aware of any major activity after that. Yeah, I don't have a good answer to that question, unfortunately. Yeah, but that's a great question. I think it somehow reminded, because that was a time when everyone was building dashboards and everyone wanted to connect to the internet, and the industry 4.0 was just getting started, that hype, right? So that was a reminder that still don't be overconfident connecting your network to internet, it requires much more due diligence before adopting something based on the hype. One shift which I can recall, or which I can use to answer your question, is that instead of using bidirectional data acquisition strategies like is there in OPC UA, there was something called MT Connect, which was introduced. And so MT Connect is a single directional data connection protocol. So using that, you can only read only from the machine, but you cannot write back to it. So that started gaining prominence, after that, I think in the same time zone.
Okay, I think we have to stop here because we are 5 minutes behind our schedule. Thank you very much.